Welcome to the fourth video in my series on proving the twin primes conjecture. In this video, we craft two proofs for the twin primes conjecture. Method 1. Actuals classic divergence to infinity proof. Theorem 4a. Infinitude of the twin primes. The sequence of twin prime counts, theta sub m, tends to infinity as m tends to infinity. In symbols, equation 4a, the sequence theta equals q sub m squared minus 1 all over 6, the quantity, times I sub m tends to infinity as m tends to infinity, where m is a member of the set of natural numbers greater than 2. This formula contains our link to the prime squares in the form of q sub m squared. The proof that follows includes the formula 4 more times. Rather than repeating the formula each time, when I come to it, I will simply refer to it as our formula. Definition 19. The sequence theta is the sequence of actual twins counts in which each theta sub m value is the twins count up to the square of the basal prime q sub m. We learned in the previous video in equation 3e that theta equals k times I. Definition 20b. The sequence I sub m is the sequence of fractions which multiply k sub m to yield theta sub m. Definition 20. The sequence k sub m is a sequence of j's, that is, motif table row numbers, for rows that contain basal prime squares, which we designate as q sub m squared. We also learned in lemma 3a, the infinitude of k, that k can be written in terms of q squared according to equation 3b. So in our formula in the proof, we have simply substituted the right side of equation 3b for k sub m. Definition 22. A basal prime is a prime q that acts as a principal factor of numbers up to the squares of primes greater than or equal to q. And as a reminder, let's also include the definition of a principal factor. Definition 2a. The principal factor for a given number n is the lowest prime factor q such that q is greater than 1 but less than n. Thus, in our formula, we have the twins counts in terms of the prime squares, establishing our link that makes it possible to prove the twin primes conjecture. The sequence I, of course, constitutes the actuals equivalent of the fractions by which k must be multiplied to subtract out the blockages in our CAP formula that approximates the twins' distribution so accurately. With these things in mind, let's continue. Proof. Let upsilon, a member of the set of natural numbers greater than 0, be arbitrary. We say that sequence theta sub m tends to infinity if for every upsilon greater than 0, there is an integer capital M such that theta sub small m is greater than upsilon whenever small m is greater than capital M. Let capital M be an integer satisfying q sub capital M is larger than the floor function of the square root of 6 upsilon over I sub capital M, the quantity plus 1. Note that the floor function simply indicates that the result is rounded down to the nearest integer. Also notice that this second formula is simply our formula above, rearranged to solve for q, in which upsilon has been substituted for theta. Then small m greater than capital M implies that theta sub small m equals our formula sub small m greater than our formula sub capital M greater than upsilon. Hence we have shown that in symbols, for all upsilon greater than 0, there exists capital M, a member of the set of natural numbers, such that for all small m greater than capital M, our formula sub small m is greater than upsilon. Or in words, however large upsilon may be, there is a point in the sequence theta sub m such that beyond that point all the terms are larger than upsilon. Thus, the sequence theta, which equals our formula, tends to infinity as m tends to infinity, as required. Let's take a moment to illustrate the proof's logic with an example. We set epsilon to 100,000 and then search for the correct value of capital M in accordance with Theorem 4a. We locate the first capital M at which Q sub capital M meets the condition specified in the theorem, which is as follows. This means the first value for which column 2 of the table minus column 3 of the table is positive. So column 4 of the highlighted row, which is the row for capital M equals 590, has positive 6. All of the entries in column 4 prior to that row are negative. Note that from the highlighted row onward, all values for theta sub m are greater than 100,000 as required. We can also illustrate the theorem's logic on the graph of actual twin counts itself as shown here. So, at capital M equals 590, Q sub capital M equals 4,297, theta sub capital M equals 100,246, and all theta values for small m greater than 590 are greater than 100,000 as required. As you can see, this proof, based on real analysis, is rigorous and uses tried and true methods of proof. What makes this approach possible is the mathematical link between the prime twins and the prime squares that our work with motif tables reveals, namely that a principal factor does not become operative until it's square. Up until its square, a given principal factor can be ignored, but starting at its square, it must be included in the formula for counting the prime twins. Method 2. Dominant term proof. Theorem 5a. Infinitude of the prime twins. The sequence of prime twin counts, theta sub m, tends to infinity as m tends to infinity. In symbols, equation 5a. The sequence theta, which equals the product sequence k times I, tends to infinity as m tends to infinity. Proof. The sequence of twin prime counts, theta sub m, is a sequence of actual twin counts up to successive basal primes, that is, the greatest principal factors squared, in other words, q sub m squared, and thus is indexed by the same index as the squared primes, m. The theta sequence can be viewed as the product of k times I as shown above. This relation in turn can be rewritten in terms of the basal prime squared as equation 5b. Theta sub m equals our formula. With the rewritten version, we can see clearly that since the sequence k includes the term q sub m squared, it has an exponential character. It therefore must diverge to infinity. This, of course, is the conclusion of lemma 3a, the infinitude of k. Our only question then is how does the sequence I affect the product sequence k times I? If k dominates I, then theta diverges to infinity as required. But if I dominates k, then theta converges to some finite value. We will assume that I dominates k. The sequence I is obtained by simply dividing each member of theta by the corresponding member of k, in which case we find that the resulting sequence consists of fractions that slowly approach zero. In other words, I is a null sequence. This, of course, is the conclusion reached in lemma 3b, the character of I. Now, if members of the null sequence were to drop as low as 1 over the square root of k and remain there, then from that point forward the members of theta would equal k times 1 over the square root of k, which equals the square root of k, and theta would become mostly linear rather than exponential. Nevertheless, theta would still have a positive slope, and so it would still diverge to infinity. In order for I to dominate k, its members would have to drop well below 1 over the square root of k. Thus, the ratio of I to 1 over the square root of k for a given m would have to drop well below 1. However, if we divide each instance of I by the corresponding 1 over the square root of k, we find that their ratios not only fail to drop below 1, or even to remotely approach 1, they produce instead a monotonic ascending sequence. By the time the sequence of ratios reaches m equals 19,358, the ratio has increased to 1,270. In other words, the value of 1 over the square root of k sub 19,358 is more than 1,200 times smaller than I sub 19,358. From this analysis, we can see that I approaches 0 at a much slower rate than k approaches infinity. Consequently, its effect on theta is negligible. The failure of the ratio of I to 1 over the square root of k to approach 1 and drop below it constitutes, then, a contradiction of our assumption that I dominates k. The assumption, therefore, is false. Nor is it the case that neither sequence dominates. Quite the contrary. K clearly dominates I. The sequence of twin prime counts, therefore, inherits the exponential character of the dominant k sequence. This means, of course, that theta is itself exponential and diverges to infinity, as required. So now we have a second rigorous proof that there are infinitely many twin primes. This proof, like the first one, uses a tried and true approach from real analysis. If you examine the PDF with the proofs in it by following the link in the panel below this video, you will discover that there are two more versions of the proof. Method 3 resembles the proof in Method 1, except that it does not use the actuals. Instead, it uses a lower bound based on a lambda setting of 3, indicating an assumption of 3 blockages per motif, which of course can never happen. Thus, it's a very conservative and safe lower bound that nevertheless diverges to infinity. And since the actuals will be higher than the lower bound, it follows that they too diverge to infinity. Method 4 proves that beyond a certain value of m, there will always be at least one new pair of twins between any pair of successive prime squares. Here are the 4 breakthrough discoveries that I have made regarding the twin primes conjecture. What makes all 4 of these proofs possible is the 4th discovery, the link between the twin primes and the prime squares. The best way to prove the infinitude of a set is to link that set mathematically to another set whose infinitude is already established. We learn this from Euclid and his proof that there are infinitely many primes. So, which infinite set does Euclid link the primes to in his famous proof? The integers. The proof of the infinitude of the integers is so simple that we can forget there even is such a proof. It is simply the observation that no matter how far we go out on the number line, we can always add one more integer. Euclid actually includes that proof as his link to the integers. He says, consider capital P equals small p sub 1 times up through times small p sub n. Now let Q equal capital P plus 1. At this point he has actually included the proof for the infinitude of the integers. He's saying, just as we can always add one more integer to the number line, we can add one more to P, however large P may be. He then goes on to show that Q is either prime or is divided by a prime that is not a factor of P. Thus, since the integers are infinite, it follows that the primes are infinite as well. In our case, we can prove that there are infinitely many prime squares by noting that there are infinitely many primes and that every prime can be squared. From there, we reason that there are infinitely many prime squares and every prime square has prime twins up to it as given by our formula. The prime square itself less 1, all over 6, the quantity times I. This concludes my video series on proving the twin primes conjecture. I will have more proofs and more videos, so remember to subscribe and press the bell to be notified when a new video becomes available.